Good morning, all. So this week, this is the first class. We will be starting with the review of Module 5. Okay, Module 5 already you have gone through once or twice. I think twice. You might have gone through Module 5. So this will be the review of Module 5. Okay, as you all know, Module 5 is about different type of antennas. Just a few types of antennas we are going to see in this module. Low periodic antenna, helical antenna, smart antenna, and antenna for mobile and radio communications. Okay, these are the main topics we have to study in this module. So, as university exam point of view, this will be one of the simplest modules in which you can score a lot of marks. And this module is having a 20-mark weightage also. So it will be very easy for you to understand and very easy for you to score marks also. Okay. So I think all of you might have gone through at least once. So this session will give you just a refreshment of the things what you have already seen. Okay. So we will start. So we will start with log periodic antenna. Okay. As the name suggests, log, the antenna is having a relationship between log, having a relationship with log, and it is periodic antenna. Okay. So it is a the main thing we have to see in this is a frequency independent antenna. Okay, we can use it for a wide range of frequencies. Frequency is not that much important for a log periodic antenna, and it is invented by John Dunleavy in 1952. Okay, it is like comparatively newer form in 1952 only. It has been discovered. It is invented. So, impedance, radiation pattern, and directivity remains constant irrespective of frequency. That's why it is called as frequency independent antenna. Okay, its impedance, radiation pattern, and directivity all will remain constant. Even if we are using a higher frequency, lower frequency, these things will not change. That's why it is called as a frequency independent antenna. It's also called as log periodic dipole antenna, since dipole antennas are used as elements. That is one of the main things we have to remember here. In this, the elements, the antenna elements, basically this is an array. Okay. Basically this is array only. We are discussing about arrays only. So log periodic antenna means the implied meaning is log periodic antenna array. That means so many members will be there. Number of elements will be there. Okay. So it is also called log periodic dipole antenna since dipole antennas used as elements. In this, the individual elements will be dipole antennas. What is a dipole antenna? Dipole. There will be two poles. Okay, this is a basic or simplest form of antenna which consists of two poles. It means two legs will be there for antenna, one upper length and one lower length. That's the basic thing. We have derived in second module and all. In second and third module, we have seen. Okay, dipole antenna. That basic antenna will be the elements, or the elements will be dipole antennas. The radiation will be unidirectional or bidirectional with moderate gain. Okay, with dipole antennas, we can have a unidirectional radiation pattern or bidirectional radiation pattern. Okay, and fire and broadside case. In the I think you might have will be remembering that those cases in fair and broadside case. In that we can convert the bidirectional radiation pattern into unidirectional radiation pattern. How we can do that? All those things we have discussed in contact classes also, and I think I have covered during the review of module 3 also. Like module 3 first class, it was a review of the things we already studied in module 3. In that, this particular thing I was asked, and I think one or two answers also I got. Okay. So, likewise, the radiation pattern we can convert into unidirectional or bidirectional. With gain will be moderate. It is not a very high gain antenna and not a very low gain antenna also. the gain will be moderate. Electrical properties repeat periodically with logarithm of frequency. Okay, the electrical properties repeat periodically with logarithm of frequency. That is the impedance and all those things, which depends on the electrical characteristics. Okay, or the phase leading of phase or current leads the phase, current lags behind the voltage. All those things they will repeat periodically with logarithm of frequency. Okay. It's a broadband antenna which provides large bandwidth with good directivity. This is understood only because since it is a frequency independent antenna, means what is the mean by frequency independent antenna? It can operate over a wide range of frequencies. Frequency is not that much important. But that is only the last point. Broadband antenna. That means it can operate over a wide range of frequencies, and it provides large bandwidths. That's it. Broadband antenna means it can operate for a wide range of frequencies, hence the bandwidth will be large. This all those things are same only, just some manipulation of words. Okay, and it is having good directivity. It will be having a good directivity also. So this is the basic points you have to remember with or remember about this log periodic antenna. Okay. The basic thing is this log periodic antenna. It is a dipole antenna or it's a dipole array. Okay, and it is having a relationship with log. What is that relationship? That is only we have to see now. Okay, we are just going through the frequency independent characteristics and the electrical properties and all of this antenna. Now we have to see what significance does this log term have. Okay, so we will see in the construction. Okay, in that from the construction we will be understanding about the log nature of the antenna. Size of the structure changes with each repetition by a constant scaling factor such that it expands or contracts. Okay, there lies the relationship with the logarithm. Size of the structure changes with each repetition by a constant scaling factor. One scaling factor is there. Okay. Suppose size of first element is A and scaling factor is 2. The second element will be 2A. Okay. And the fourth element will be 4A. And fifth element will be 8A, like that. The scaling factor will be constant between two elements. So if you are taking the log of these things, we will get the correct scaling factor. Okay. Like log A, log 2A, log 2 log A, 3 log A, like that it will go. Suppose length of first element is A. We are taking logarithm of that, we will get log A. Okay. Second element is 2A. Then third element is, how much it will be? It will be 4A, like that. And if A is also 2, the size of first structure A, that is 2. Then the scaling factor, that is also 2. The first element will be 2. Second element will be 2 into 2, that is 4 or 2 square. The third element will be 2 into 2 into 2, that is 2 raised to 3, then 2 raised to 4, like that. Okay. If you are taking the logarithm of this, we will get log 2, 2 log 2, 3 log 2, 4 log 2, etc. That is the significance of logarithm here. Okay. We are taking the logarithm of this, we will be getting a continuous series. Okay, like 1, 2, 3, 4. Okay, 1 log A, 2 log A, 3 log A, 4 log A, like that. So, how the dimensions are increasing? That is the next point. Dimensions increase in proportion to the distance from the origin. Okay, as the distance from the origin increases, the dimensions also increases. Dimensions means dimensions of the antenna elements. Okay, we already seen that it is a dipole antenna and each element will be a dipole. So these dimensions of this dipole, they will increase in proportion to the distance from the origin. That means as the distance from the origin increases, the dimensions also increases. It is fed by a balanced two-wire transmission line at the narrow end. that is the thing here. Like as you already seen, this size of the elements are going to increase from one end to another. Okay, so we will fix one end as the origin, and we will fix the elements in such a way that the dimension should increase in proportion to the distance from origin. That means as the distance from origin increases, the dimension also will increase. Okay, so where we have to feed this antennas, or where we have to give the feed for this array? The answer is it is fed by a balanced two-wire transmission line at the narrow end. So origin will be the narrow end. There we will give the feed. Okay. Since we are using all the antenna elements are, which type of elements we are using here? Which type of antenna we are using here? We are using dipole antennas. Okay. So each elements are dipole antennas. Okay. Here in origin, one small dipole antenna will be there, and the size of the dipole antenna will increase towards the other end. Okay. And we are giving the feed at the origin. So since members are dipole antennas, we have to give two-wire transmission line feeds. Okay. Dipole antenna means two poles are there. Okay. So for that, we have to give a two-wire transmission line feed. That's it. And where we have to give that? At the narrow end or at the origin. The length of the dipole increases along the antenna such that included angle alpha remains constant. That is another concept. Okay. The length of dipole increase along the antenna such that included angle alpha remains constant. What is the included angle? We will see. See. In this, it is clear. Okay, so here you can see this is the arrangement, or this is a possible arrangement of a log periodic antenna with dipole antennas. Okay, this is the first dipole, that is from the origin. So this angle is 2 alpha. This entire angle is 2 alpha. So alpha means alpha is the angle made by array axis and this edge. Okay, so this is alpha, and this angle will be constant. Or if we are drawing a straight line, all elements should, means top portion of all elements should fall on that straight line. Okay, and here also this is also alpha, and this is also alpha. So this angle should preserved, and this angle also should be preserved. In such a way, we have to deal with the arrangement. Okay, so here you can see this is shown as Rn and Rn plus 1. Rn is the distance of nth element from the origin, and Rn plus 1 is the distance of n plus 1 element from the origin. And if you are taking the difference between the two, Rn plus 1 minus Rn, we will get separation between n plus 1th element and nth element. Okay, this is a separation between n plus 1th element and nth element. And one more thing you can see here, this is Ln, that is the length of nth element, and Ln plus 1, that is the length of n plus 1th element. And if you are taking the ratio of these two, ratio of n plus 1th element to nth element, we will be getting the scaling factor. Okay, it is simple things only. Then you can see Dn, that is the diameter of nth element, and Dn plus 1 is the diameter of n plus 1th element. And one more thing is there, Sn. Sn is the separation between, or spacing between the antenna elements, spacing between nth antenna. Okay, that means it is a dipole antenna. So this is one pole and this is another pole. There is a spacing between these two. Okay, so if we are considering the nth antenna, the spacing between the two legs or the spacing between the two poles is denoted as Sn. Okay, and this is Sn plus 1. And you can see that the spacing between the individual elements or individual poles are increasing from one end to the other. Okay, so just remember this basic diagram so that you can write all these explanations. Okay, from just by remembering this picture, okay, this diagram, you can write all the theory regarding this. Okay, so that's the basic thing we need to do. There is no need to remember each and every part. Just remember the diagram. From the diagram, you can expand and you can express in your own language. That will be better. Okay. So we will go further into that. There are two types of arrangements. The first one is a straight line connection. The straight line connection means these two, that the two poles are arranged in a straight line. Okay. Second one is the crisscross connection. Crisscross connection, as the name suggests, the feed to the first element, upper pole of the first element will be given to the lower pole of second element, and vice versa. The feed of lower element of the first will be given to upper element of second, like that. So the crisscross connection, the straight connection, all lower elements will be connected through a single line, and all upper lower elements will be connected with another single element. Okay, so these are the two possible type of connections. Okay, so next we will see some mathematical analysis, just simple things only. Relationship between the length and distance from origin, that is given by, we are just taking the ratios r1 by r2. Okay, where r is the, as you can see, you just see this, where r is the distance from origin, rn is the distance of nth element from origin. So that is only shown here. R1 means distance of the first element from origin, R2 means distance of second element from origin, likewise. So R1 by R2 will be equal to R2 by R3. That ratio they should preserve. Okay, that is equal to Rn by Rn plus 1. That is equal to tau, where tau is the scaling factor. Okay, and tau should be less than 1. Okay, how can we justify that? Tau should be less than 1. Okay, we will see the next equation also. Again, this tau is equal to L1 by L2, L2 by L3, etc. up to Ln by Ln minus 1. Okay. So, what is that Ln? Ln is the total length. You can see from this diagram, you can see Ln is the length of nth elements. Okay. Like you should understand the difference between Sn and Ln. Sn is the spacing between two legs. Okay, Sn is the spacing between two legs of nth element, and Ln is the entire length of nth elements. Okay, so here we are going to say that there is a relation between this Rn and Ln, or the ratio between Rn and Rn plus 1 will be equal to Ln and Ln plus 1. That is our basic idea. We can see that Rn divided by Rn plus 1 is equal to tau, which is again equal to Ln divided by Ln plus 1. So Ln divided by Ln plus 1 means the ratio of length of nth element divided by n plus 1th element. Okay. So we will analyze that. Ln is the length of nth element and Ln plus 1 is length of n plus 1th element. Which will be higher? Length of nth element or n plus 1th element? Which will be higher? It will be higher. Length of nth element or length of n plus 1th element? Which will be higher? Yes, n plus 1. N plus 1th element. That is only higher. Okay. So from that, what you can say about tau? What will be the value of tau? Whether tau will be greater than 1 or less than 1. Just see. Yes, that will be less than 1. Okay. That's why they're saying that the tau will be less than 1. And the same with Rn and Rn plus 1 also. The same ratio should maintain between Rn and Rn plus 1. Okay. That means the separation between nth element and n plus 1th element will be greater when compared to the separation between n plus 1th element and n minus 1th element. Okay. So Rn and Rn plus 1. What is Rn? Rn is the distance of nth element from origin. Okay. And Rn plus 1 is the distance of n plus 1th element from the origin. And if you are taking the ratio of these two, you should get tau. Okay. The tau will be having a value which is less than 1. So that gives us this idea. Okay. That means anyway we know that n plus 1 Rn plus 1 will be higher than Rn. So if we are taking a ratio of Rn by Rn plus 1, we are going to get a value less than 1. And the thing is, the particular thing here is that should be equal to tau. In such a manner, we have to arrange the array. Then only we are going to get an array like this. Okay, or a log periodic array. Okay. So let me take your attendance. Okay, my online attendance is not working. Can anybody just write down the names and just send me like we did in first class? You can see almost 92 people are here. Can anybody just write down their names and send me? Nobody is there. Anybody is listening actually? No, I was just asking, can anybody? No, it's not like that. Can anybody ആർക്കെങ്കിലും ഈ 91 ആൾക്കാരുടെ പേര് എഴുതി ഒന്ന് അയച്ചു തരാൻ പറ്റുമോ എന്നാണ് ഞാൻ ചോദിക്കുന്നത്. അതർവൈസ് യു വിൽ ബി വേസ്റ്റിംഗ് എ ലോട്ട് ഓഫ് ടൈം ഇൻ ബിറ്റ്വീൻ. Nobody is ready. So what will be? Okay, do one thing. Just all of you just comment your name and roll number. Okay. All of you just comment your name and roll number. Based on that, I will be giving the attendance. Okay. So in between, we will continue with the presentation. So, as we have seen already, this scaling factor we have seen, then spacing between the elements. There is a relation between the spacing between the elements and the length. Okay. S is the spacing between the elements. So, Sn or Sn plus 1 divided by Sn is equal to Ln plus 1 divided by Ln. Okay. So, that is equal to 1 by tau. 1 by tau is represented as k. This is also very like simple thing only. As we already seen that Ln divided by Ln plus 1 is equal to tau. The inverse of that Ln plus 1 divided by Ln will be 1 by tau. Okay, that we can understand. Then how it is related to Sn plus 1 and Sn? For all these things, you just need to remember the image. Okay, just remember the image. See, here we can see that the separation is increasing. Okay, separation between the elements are increasing. So just come here. Sn plus 1 divided by Sn. You can see that Sn plus 1 is more than Sn. That we can see. So what will be this ratio? Sn plus 1 divided by Sn. That ratio should be greater than 1. Okay, since tau is less than 1 by tau will be greater than 1. So we can say that Sn plus 1 divided by Sn is equal to 1 by tau, which is again equal to Ln plus 1 divided by Ln. This is the things, these are the things we need to remember while constructing a log periodic antenna array. Okay, so the distance, the separation between the elements should also increase with respect to tau only. Okay, and as you already know, the individual element size should increase with respect to tau. Okay, then the distance from the origin of individual elements, that also should increase with respect to tau, and separation or spacing between the elements should also increase with respect to tau, where tau is the scaling factor. If we are considering all these factors, we can construct a good log periodic antenna array. Okay. Then element spacing relationship is given by delta is equal to dn divided by 2ln. Okay. So that is just a relation between element spacing and this ln. Okay, that is individual element length. So it is having 3 regions of operations. So those 3 regions are given by inactive region, active region, and reflective region. Okay. So basically 3 classifications: inactive region, active region, and reflective region. This inactive region is also called as included transmission line region. Okay. In that, 2 further classifications are there: unloaded transmission line region, loaded transmission line region. That are the 2 sub-classifications inside inactive region. So inactive region is basically a capacity region, and active region, that is basically a resistance region, and reflective region, that is basically an inductive region. Okay, that are the main 3 regions of operations of this log periodic antenna. So first we will see unloaded transmission line region. So that is the first classification in the inactive region. Okay. Here antenna elements are short compared with the resonant length. So normally lambda by 2 antenna is the resonant antenna. So lambda by 2 we are taking as the resonant length. So antenna elements are short compared with resonant length. That means the length of elemental antenna, generally we can say it as L. L will be much less than lambda by 2. So as I already told, this can be treated as a capacitive region. So here elements presents relatively high capacitive impedance. Okay, since this L is much shorter than lambda by 2, these elements can show. That means these elements are located very closely, we can say. Okay, so these elements are having relatively high capacitive impedance. So it can happen like high capacitive impedance can occur in between. Since this L is much less than lambda by 2, we can say that the elements are somewhat closely packed. Okay, so it is having a capacitive impedance. The current is small and leads voltage by approximately 90 degrees. Okay, the element spacing is comparatively smaller. The element spacing is comparatively smaller. That is the cause of occurring this capacitive character or capacitive impedance. Okay, 2 current carrying elements are separated by a small distance, means there will be a capacitance. So the equivalent circuit is shown. This one inductance will be there and one capacitance will be there, and the capacitance will be more prominent. Okay, and current leads the voltage by approximately 90 degrees, as in the general capacitance circuit case. Okay, so basically you have to remember active region. In inactive region means that will be a capacitive region. In that, two subclassifications are there. Then one active region, that is a resistive region. Then reflective region, that will be an inductive region. So in inactive region, first thing is unloaded transmission length region. In that condition is L will be much less than resonant length or much less than lambda by 2, so that the elements are closely packed or the spacing will be smaller between the elements. Okay, so it will give rise to a capacitance, and that capacitance value will be dominant. So here current is small and leads the voltage by approximately 90 degrees, as in case of general capacitive circuits. Next one is the loaded transmission line region. This is also the second classification within the inactive region. So inactive region is basically capacitive region. Length and spacing are short compared with the resonant length. Here it is short, but not too short. Okay. You can say L is less than lambda by 2. L is not much less than lambda by 2. L is less than lambda by 2. Transposition of transmission line is introduced, causing a first reversal. Okay. Here you can see that transposition. That means transpose. Okay. This transpose is causing a phase reversal. So phase reversal means what? Phase will be reversed. Okay. In first case, unloaded transmission line region, the phase was just 90 degree as in the case of general capacitive networks. But here, since the length is not that much too short, that capacitive effect won't be that much prominent. Okay. So a transposition of transmission line is introduced. That will cause a phase reversal. So adjacent elements are nearly 180 degree out of phase. Okay. Here also, since the capacitive effect is there, but not that much prominent as in the case of unloaded transmission line region. So here transposition of transmission line is occurring due to the particular spacing. That means that the spacing is not too short and not too large. Okay, so it can cause a 180 degree phase shift between the adjacent elements, and current leads by pi minus beta d, where d is the element spacing. Okay, b is 2 pi by lambda. Okay. And if just put this in pi minus beta d, you just put beta is equal to 2 pi by lambda and d is equal to lambda by 2. What you are going to get? Just substitute in this equation, beta is equal to 2 pi by lambda and d is equal to lambda by 2. What you are going to get? It will be 0. Okay, so if we are spacing at exact multiples of lambda by 2, we will be getting 0 phase difference between current and voltage. Okay, so here that is not the case. The length is less than lambda by 2. So as the spacing. Okay, so we can say that the equivalent circuit can be written like this. The CA is for that represents the transposition of transmission line. So one additional capacitance will also be there. Then what will be the effect of two capacitances connected in parallel? There we were having one capacitance only, then it was just continuing as the number of cases increase, the number of elements increases. Here we are having two capacitance, and that too you can see one line here. Okay, so you can see one line here. It is further connected to another capacitance. So these things will limit the entire value. Okay, the entire value will be limited to a particular constant value. So finally, we can say it as a capacitive circuit, but the effect of capacitance will be not prominent as in the previous case. So here the main thing is the adjacent elements are 180 degree out of phase rather than 90 degree. That is due to transposition of transmission line. Okay, that is these are the two capacitive regions basically. That means these are comes under the inactive region, unloaded transmission lane region and loaded transmission lane region. The inactive region is finished. Okay. Next one is the active region. Active region is what? That is the resistive region, as you can see here. Okay, on resistance you can see here. And I already told in the previous case to substitute L is equal to lambda by 2. Here I have told you D, just substitute D is equal to lambda by 2 for L. Both are same only because all the ratios are giving our top. Okay. So both will be same only. So this is if at that particular point of time you are getting 0. The phase difference between current and voltage 0. What does that mean? The circuit is purely resistive. If it was capacitive or if it was inductive, there would have been some difference in the phase. Okay. But here that phase difference is not at all there. So we can say that if phase difference is not there, the resistance is purely, means the circuit is purely resistive. So this is the for that we have to keep L is equal to lambda by 2. This is the central region of the array. Okay, E plane radiation is maximum, and element impedance have resistive component. Current is large and almost in phase with the voltage, producing a strong radiation in the backfire direction. Okay, so in the central region of the array, the length L will be equal to lambda by 2. At this region, the radiation will be maximum and the impedance will be resistive, and there won't be any phase difference also, and current is large and almost in phase with the voltage and producing a strong radiation. Those things it is understood. Okay, current is in phase, and from the central portion only maximum radiation will come. The last one is the reflective region. That means this region is towards the far end, where L will be greater than lambda by 2. Okay, the element impedance become inductive and current lags the voltage. There, the radiation will be very low. Here you can see the circuit is equivalent, but in parallel combination, one inductance is appearing. Okay. So the applications are high frequency communication and all-round monitoring. All-round monitoring means it can use for any frequencies. Okay. So the regions of operations I will just explain with this figure also. See, here we can say the initial stages. Initial stages are having capacitive nature, since this L is much less than lambda by 2. Okay, the initial stages L will be much less than lambda by 2, and that will be inactive region and unloaded. Okay, in inactive region, unloaded and loaded, two regions are there. In unloaded, L will be much less than lambda by 2. That can be treated as the initial regions. Then as the length increases, we can say that L becomes comparable to lambda by 2. That is the loaded region inside first classification. Okay, inside inactive region, when L becomes comparable to lambda by 2, that becomes loaded region. Then when L is equal to lambda by 2, when L is equal to lambda by 2, at that particular point, that will be the central point. Okay, that will be the central point of the array. That will be the active region. Okay, then after that, towards the far end, you can say this portion. This portion, L will be greater than lambda by 2. That is the reflective region. Okay, so this is the thing with three regions of operations of log periodic antenna. Okay, so we have already seen this those three regions, and the applications are for high frequency communication and for all-round monitoring. Okay, so this is a log periodic antenna. You might have seen this type of antennas in radio stations and all, and we have seen, I think most of the current radio stations are using this type of antenna only for their that FM stations. they are using this type of antennas only. I think in Calicut and all, you can see in that Radio Mango, they are using this. I think yes, they are using this type of antenna. If I'm not wrong, I've seen once or twice their antennas. Okay. So this is a practical implementation of that. You can see both the elements and the lengths are increasing, and the feed will be given at the origin or where the elements are short. Here the feed will be given, and you can see the separation. You can see here these two feeds are almost joined, but as it comes to this side, you can see the separation is going on increasing, and that will be proportional to the length of these two. And the separation between the arrays means individual elements also. See here, they are close, and while coming here, see here, they are far apart. Okay, so that all those characteristics you can see in this image. See, this is the FM antenna. Okay, dipole antenna. You can see these are the individual elements. Okay, 1, 2, 3, 4, 5 elements are there in this. So individual legs you can see, and you can see the lengths also. It is increasing. Okay, increasing in a straight line, so that the included angle alpha will remain constant. Okay. So that's how the practical applications are coming. So next is the helical antenna. I think this helical antenna we will take in the next class. Okay. So thank you for your cooperation. Okay, thank you. Okay, it was my birthday today, so thank you for wishing me. Yes, thank you. Okay, the first thing I did on this day is taking online class. So I think the next year completely I have to take online class. I don't know.